Thanks. I'm going to be talking about some efficient methods for generating higher derivative corrections to gauge theory and gravity through some double copy methods. And this is based on work I've done with John Joseph and with Laurentiu Rodina. Okay, so I'm going to start by thinking really broadly about how we construct the predictions of our favorite theories from building blocks. And double copy really invites us to think about these amplitudes as built up from adjoint numerators. So supergravity from super Yang-Mills, or Born-Infeld from Yang-Mills and nonlinear sigma model adjoint numerators. And of course, this structure has led to incredible discoveries about a whole wealth of connections between lots of different theories. But today we're going to go in a slightly different direction with it and ask not just how we can construct amplitudes from adjoint numerators, but also how we can construct the adjoint numerators themselves. So guided by the light of algebraic structures, we're going to introduce the concept of using composition rules to generate new adjoint numerators by combining two known adjoint solutions, or similar constructions for structures beyond adjoint. As an example here, I'm taking one of our favorite scalar theories to deal with that I'm going to introduce called the simple scalar, corresponds to this action. So it's just adjoint scalar coupled to a massless vector. If you take the adjoint numerators for the simple scalar and combine them in a particular way, you generate the adjoint numerators of the nonlinear sigma model. So we're not double copying to get a nonlinear sigma model amplitude, we're really constructing the numerators. Using these sorts of composition methods, we're going to try and extract the simplest, most fundamental pieces of our physical predictions, and then combine and compose them in creative and interesting ways to generate new amplitudes like higher derivative corrections. So specifically, we're going to focus on higher derivative corrections to gauge theory and gravity at 4-point and 5-point tree level, but we're going to do so in a functional graph-based way, just with an eye towards applying these ideas to multi-loop. So of course, these higher derivatives are of interest as renormalization counterterms or to EFTs or string theory. We've seen a lot of good talks today about these sorts of things. Higher multiplicity is also particularly of interest because they're going to make loop level accessible via unitarity. What we're going to see is only a really small number of building blocks are needed to construct these corrections, and that novel color kinematic dualities will emerge at 5 points. Okay, so first I'm going to go through a quick overview of how we generate 4-point corrections to maximal super Yang-Mills. What we're going to do is construct amplitudes, leaving the super Yang-Mills adjoint numerators untouched. They already obey our Susie Ward identities. Let's just leave the external state information in there. So what we're going to do is encode the higher derivative factors in something I'm calling a modified color factor, or CHD. And this is an adjoint function of both color information and scalar kinematics. So we need to figure out how to combine color and scalar kinematics into adjoint objects. And to do this, we sort of have a pretty good indication of the types of structures we want to deal with by looking at color. There's FABC type color for adjoint, and we also have totally symmetric DABCD type color. So correspondingly, we also have permutation invariant scalar kinematics, these sort of classic combinations of the Mandelstam invariants. And we have adjoint scalar kinematics. So there's the simple scalar theory that I mentioned earlier. The adjoint numerators are U minus T for the S channel. And that's also the unique solution to imposing adjoint constraints on an Onsoff linear and Mandelstams. And there's the nonlinear sigma model. And we can actually find all these scalar corrections as given from compositions of just the simple scalar. Also, there's vector building blocks. I'm not going to talk about them as much today just because they're harder to write down. Okay, so now that we have those building blocks, we can think about how to compose them into adjoint solutions like CHD. So if we have two adjoint numerators, J and K, we can combine them by taking their T channels minus their U channels, and that'll generate for us a new adjoint numerator, like simple scalar with itself gives nonlinear sigma model. And we can take those adjoint numerators and generate a permutation variant by summing over all channels. We do this with simple scalar and nonlinear sigma model, we just get STU. The structures close really quickly to the ones we already recognize. You can also see here how we can fit totally symmetric color into an adjoint object like CHD. Okay, so we take all the building blocks and all the composition rules and combine them. We actually find that for all those pieces, there's only 3 independent structures that we can make for CHD. And then if you sum those up over all orders with appropriate numerical coefficients and put it next to super Yang-Mills, we reproduce the open superstring to all orders in alpha prime. And here we have it done perturbatively, but we can also uncover these structures within the resummed expressions for the open superstring. We can also double copy to n equals 8 compatible gravity counter terms. and they turn out to be proportional to just the maximally supersymmetric gravity amplitude times scalar permutation invariance. Okay, so just in summary, at 4 points, we see only 3 structures combining all our color and scalar building blocks to get CHD correction factors. If you want to generalize past super-Yang mills, there's a total of 8 independent vector structures. And if you take 4 of them in some specific linear combination, alongside these CHD corrections, you can reproduce the open bosonic string. And for more details on 4 point, you can see this paper that I did with JJ, Laurentiu, and Zhenpeng. All right, so now we're actually going to get to really focus on the priority of this talk, which is 5 points. And this is work in progress with JJ and Laurentiu. So what we find at 5 points is a whole wealth of different algebraic structures. And this gives us a whole bunch of options for composition rules, but we're actually still going to find that just like at 4 points, where the simple scalar gave us everything we wanted, we're going to find a single scalar kinematic building block at 5 points as well to generate all the factorizing corrections we care about. And also we're going to see all these new algebraic structures will give rise to associated color kinematics dualities in our local amplitudes. Okay, so first we really need to understand the algebraic structures at 5 points, and they sort of neatly fall into different graph topologies depending on the vertices they're associated with. First off, we're going to consider cubic graphs and the really standard adjoint relations. So there's no surprises here. Adjoint relations at 5 points are going to be defined by having anti-symmetry on all 3 of our cubic vertices. And it's key to note here that at 5 points for these half-ladder graphs, anti-symmetry around the central vertex also can just be interpreted as picking up a minus sign when you reflect your graph. The adjoint structures also obey Jacobi relations on both of their internal edges, which I have sketched out here. Now we're going to introduce something new that we're calling relaxed adjoint. And it's going to seem a little bit arbitrary right now, but it's going to turn out to be vital for us constructing these corrections. So this is an important thing to remember. So relaxed adjoint structures are still going to obey Jacobi relations on both edges, just like adjoint. They're still going to have anti-symmetric outer vertices, just like adjoint, but their central vertex is going to be totally symmetric. So no sign flip when you flip the graph over. And people who are a little more familiar with color structures might look at this and think we can associate it directly with a contraction of FABCs and DABCs of this form, F3, D3, F3 is shorthand. And it's true that F3, D3, F3 obeys these vertex relations, but it actually doesn't obey Jacobi identities. They obey looser constraints. So really it's like we're looking at a stricter subset of F3, D3, F3 constraints and sort of like specifying down to relaxed adjoint. And we're going to see that Jacobi relations are really going to win us a lot in this structure. So that's why we're specifying from this. Okay, next up we have a notion of hybrid structures. These have one cubic vertex that's anti-symmetric, one quartic vertex that's totally symmetric, and they also obey 4-term identities, the way you could maybe call Jacobi a 3-term identity. And these you actually can associate with sort of the natural color factor D4F3. D4F3 does obey hybrid constraints. And finally, of course, you can have totally symmetric permutation invariant structures at 5 point, no surprise there. All right, so now it's time to think about both the color and scalar building blocks we have at 5 points for each algebraic structure. And we're going to start with relaxed instead of adjoint, and that reason will become clear soon. So relaxed, again, just as a reminder, Jacobi on both internal edges, anti-symmetric outer vertices, but it's this weird central vertex that's symmetric. So as I said before, it's not quite F3, D3, F3 color. You need a linear combination of these objects in order to make it satisfy Jacobi. Scalar kinematics is really where relaxed adjoint structures have their day. And it's because the relaxed constraints admit a solution that's linear in Mandelstam invariance, this R1 combination right here. And this is a pretty unique thing at 5 points in that I can write it down very comfortably on a slide. It's going to turn out to be really vital for generating lots of different solutions. But even if we aren't focusing on gauge theory solutions and are just interested in this curious relaxed structure, we can get a lot done with just this linear solution R1. If we compose R1 with itself to make a new relaxed solution, we actually end up getting all possible quadratic solutions to the relaxed constraints. And you can repeatedly compose with R1, so on and so on. And you get all the solutions you could ever want for relaxed constraints. And then finally at ninth order, the structures close to the lower point solutions times permutation invariance. So R1 gets you everything. Next up, adjoint structures. So of course, adjoint color, you have F3, F3, F3 type contractions of FABCs on each vertex. But interestingly, the adjoint constraints actually admit a second solution in color, and it's this combination of D4 F3 structures. And there's no way to re-express this as F3, F3, F3s. And this was really surprising to us at first, but it actually turns out to be crucial for capturing some of the factorizing corrections we care about. Okay, so we'll come back to this color structure soon, but then we can look at adjoint scalar kinematics. And the first solution to the adjoint constraints is actually cubic and Mandelstams. And if we wanted to, do the same thing we did at 4-point, where we take our simplest scalar solution and repeatedly compose it to get solutions at each order, at 5-point, since we start out with cubic, we'd only be able to access a 3rd order correction, a 6th order correction, 9th order, and so on. And that's obviously not very advantageous. That is why relaxed constraints are so important. Because relaxed constraints give us a linear solution, repeated combination or composition with that linear solution will allow us to climb up rung by rung on a ladder of corrections. That's why we care so much about it, is linear can get us everything, whereas cubic cannot. But we can actually still, if we want to talk about adjoint kinematics, do so by just repeatedly composing with R1 as the only building block. Since this was already made of R1, you can get all the adjoint solutions, and they also close. All right, finally, we have permutation invariant structures. For color, you have your standard DABCDE type totally symmetric color. For scalar kinematics, just like at 4 points, you can generate a permutation invariant by taking an adjoint dressing for a cubic graph and summing over all graph orderings. We can do the same thing here, but again, since we only have cubic and up for adjoint, we may as well start with relax, and you can do the exact same thing. Just take that dressing and sum over all 15 cubic graphs, and we use that and we're able to generate all the permutation invariant structures we want. And all you need is R1, and also eventually these structures also close by 10th order. You just have products of lower point solutions. All right, so now we can finally start constructing amplitudes. So I'm going to consider our higher derivative corrections to maximal super-Yang-Mills, not in the vector theory, but in an equivalent scalar theory where I've replaced super-Yang-Mills for the time being with the adjoint color of a second gauge group. So it's just corrections to the bi-adjoint scalar. And I'm only doing that because when I consider factorization, I don't want to have to think about a state sum. And at the end of the day, I'll just sub this back for super-Yang-Mills. But anyway, when we do this factorization condition, we'll want our 5-point amplitude to split into a 4-point amplitude. And these are the types of corrections we made out of CHD, those 3 independent structures at 4 points. We already know what these amplitudes are, and a 3-point amplitude. And it actually turns out that this is the uncorrected bi-adjoint scalar. There aren't any corrections at 3 points to the bi-adjoint scalar. And that's because for on-shell 3-point kinematics for real momenta, all the Mandelstam invariants vanish. So there's no way to dress it with scalar corrections. Okay, so we can use this factorization condition to guide how we're going to construct the 5-point amplitudes. So the 3-point bi-adjoint scalar uncorrected is just FABC. 4 points, the color structures we saw were standard adjoint and D4. So in our 5-point amplitude, we have to marry these color structures. So we're either going to end up with F3, F3, F3 color or D4, F3 color. And luckily for us, both of those are found in our adjoint color solution. Remember that weird linear combination of D4, F3? This is where it matters. So we can take both those adjoint color solutions and repeatedly compose them with our linear relaxed solution in this sort of nested fashion to get to the order and mass dimension we want a correction for, and then take that object, which is automatically going to be adjoint just by the nature of the composition. That's how we define the composition. And then fix it on this factorization condition. And we find all the associated solutions we want as guided by 4 points up through all these orders for both types of color structure. A couple quick notes before we move on are that the composition structures, the nested ones, close past 7th order. We don't need to worry about any new ones. And also the D4 F3 amplitudes are really coming from that adjoint D4F3 solution. We took those amplitudes and we tried to striate them instead along the like hybrid D4F3 algebra where you had the 4-term identities, and it wasn't compatible. So you really do need that weird D4F3 adjoint solution.
5 minutes
Okay.
left.
Thank you. All right, so finally we can move on to local contact corrections. So sort of like a 5-point contact type term. And first, the way we were constructing these, and again, I'm working in this by adjoint scalar correction theory, is you have your adjoint color for the second gauge group. Then you have adjoint functions encoding the higher derivatives, Sij, and some type of color Cx, and that can be any of the color structures that we care about. And this type of color, Cx, is what survives the double copy with super Yang-Mills. We throw this out, but this shows up in the final amplitude. And what we can do is construct these adjoint functions of Sij and Cx by similar nested compositions to how we did at factorizing. Just repeatedly taking R1 with this color to make something adjoint. And then what you do is you sum over cubic graphs, and then you demand to get this contact interaction that the propagators cancel. And at 4 points, that's a really trivial thing to do. You just make each numerator proportional to the propagator in the denominator. But at 5 points, the same pole appears in different graphs, and you can get non-trivial cancellations between the graphs. So this is actually sort of a computationally intensive process, getting these propagators to cancel at high mass dimension. But we see something really interesting if we choose to striate not along this adjoint color that we throw away in the double copy, but instead along the color that survives the double copy. So let's pick, just for Cx so we can be specific, let's pick D4F3 color. So I take that amplitude and I instead rewrite it as a sum over the graphs that D4F3 cares about. Naturally, D4 is associated with a quartic vertex. So there's 10 graphs instead of 15 for this sort of form. And what I see is the coefficient of each color factor D4F3, I'm calling it Y here, displays two really interesting properties. The first is that it's manifestly local. I'm no longer dependent on cancellations between the graphs to get my contact interaction. The second is that it obeys the exact same algebraic properties as D4F3, those hybrid constraints, the vertex symmetry and antisymmetry, and also the 4-term identities. So we see a D4F3 type color kinematics duality emerge in this amplitude when we striate along D4F3. And what this gives us is a really powerful method for constructing these amplitudes. So rather than start off with the adjoint striation, we start off with our alternate striation like D4F3. What we do is we sum over all the graphs, and what we do is we dress each D4F3 color factor with some function y that's fixed on X-type algebraic constraints. And here X is D4F3, so fixed on hybrid algebraic constraints. And you could do that brute force with an ansatz, but since we know we want it to be hybrid, we may as well use compositions to hybrid forms to ensure we're automatically writing down things that obey hybrid constraints. And you can think of repeatedly composing scalar kinematics like R1 with the other thing you need to see in this Y function. We have to put the second gauge group's color factor somewhere. It's hidden in Y. So you can just repeatedly do some sort of nested composition like we did for factorizing structures with R1 over and over again with this, and constructively always make sure you get something that's dual to the D4F3 color every time. So this gives us our D4F3 dual form of the amplitude, and it's manifestly a local contact term like we wanted. Then what we can do is look at the color that's hidden in here in this Y function, striate along that instead, put it into a DDM basis. The coefficients of each factor are then ordered amplitudes, and we fix those on the m-3 factorial or BCJ relations to impose adjoint color kinematics duality. So in this sense, these amplitudes are doubly dual. This one obeys D4F3 duality and adjoint color kinematics duality, just depending on how you striate it. What you can do is, just like at 4 points, you can take both your factorizing and your local contact amplitudes and fix their coefficients to the 5-point open superstring. And what we see is that even though we had all these color structures appearing for our local contact corrections, the coefficients of these amplitudes vanish in the open superstring, and that's because the open superstring amplitudes obey this reflection identity, where if we swap the order completely of the arguments, we pick up a minus sign. And these color factors just aren't compatible with that. You can think as an example, D5, all the ordered amplitudes are the same, so they're not going to satisfy this, of course. Okay, so what's up next for us with this sort of stuff? We're going to continue looking for this sort of structure and small number of building blocks at loop level, hoping to see composition rules at multi-loop level as well. Also interested to see how we go from our S matrix predictions back to operators. And as a specific example, in those contact corrections, D4F3 is crying out to be replaced by a vector that obeys D4F3 hybrid constraints. And we have found that sort of vector via an ansatz, but the question remains, what's the corresponding gravity theory when you make this replacement in the double copy? Okay, just as a quick summary, we saw that you only need a really small number of building blocks. It's the simple scalar at 4 points and the linear relaxed solution at 5 points to generate towers of higher derivative corrections. And this sort of composition method gave us a constructive alternative to writing down ansatz. And finally, we saw novel color kinematics dualities emerge in our local corrections that made them a lot easier to write down. Like this amplitude had both adjoint color kinematics form and a manifestly local D4F3 color dual form in the same amplitude. All right, thank you.
Thank you very much for a nice talk. Are there any questions? Joey.
Hi, Suna. Thank you for a nice talk. So I have a question. So you have 4 point and 5 point vertices, and you only consider totally symmetric ones. Is there a reason for this choice? For example, it is enough for something, or it is just
yeah. So do you mean like taking something like this and dressing it with an F3 type contraction?
Yeah, I can kind of see that at 4 point, the only thing apart from the totally symmetric one is F3 one. But what about 5 point? At 5 point?
Yeah, so I think there is the possibility of having, something like this dressed with anti-symmetric factors, and it would just be like, I think how we are encoding that information is thinking about some still cubic adjoint structure, but with sufficient propagator canceling factors to sort of fit. It's like how we absorb like a 4 point contact term onto cubic graphs, essentially.
Okay. The other thing is that have you considered like at 5 points, the West Lumino Witten term, for example, in 4D, you have a 4D Leverage beta, so it's P to the 4th. That contact term, does it satisfy any of your?
I'm not actually really familiar with that term, but I think it would be good for us to look at that. Thanks. Yeah.
Okay, cool. Yeah. Thanks.
Alex?
Hi. Yeah. So I was wondering, maybe I missed it, but did you define what D4 is anywhere?
Yeah, no, sorry, I didn't. I'm just thinking about it as like a completely symmetrized trace. So like summing over like permutations S3 of color traces with labels like this. And then T4 for my 4th label, or D, or whatever you want to call it. So it's just like DABC is a totally symmetric color structure in 3 indices. This is a totally symmetric color structure in 4 indices. So just equally weighting all the traces you could write down.
So in a non-EFT gauge theory, that would be a loop correction color factor.
Yeah, right? I think so, but it also shows up at tree level in like the supersymmetric F to the 4 amplitude is dressed with totally symmetric DABCD at tree level. Yeah. So I think it's relevant in those sorts of
but
as well.
Yeah, but if I think about it as a loop level thing, at 4 points you can also have double traces, which are not totally symmetric, but just also a valid color factor that appears at the same loop order and maybe somehow is reflected in an EFT if you
Yeah,
want to.
no, I'm actually pretty interested to see how, especially as we go to loop order, multiple traces turn up. We haven't considered them at all yet, though.
Uh-huh.
And let me just point out that Jiawei has written a couple papers about double traces at tree level and these types of games.
Okay. And some operators that correspond to them, higher dimensional operators?
Yeah, so what we did was that we considered nonlinear model and just the subleading corrections, P to the fourth. So in general, there are 4 operators, 2 are single trace ones, 2 are double trace ones. And at 4 point, all of them can be generated using the composition rules discussed before. But then the next thing is 6 point. So it's beyond.
Yeah, you can also have triple traces, right?
Sorry?
At 6 points, you can also have triple traces.
Right. Yeah. But that you need to go to even higher order. They can only consider P to the fourth. So always have single or double trace.
Okay, thanks.
So we have -1 minute for the last question from James.
Yeah, so maybe this is a bit naive, but what about going to higher order tree? So, I mean, is there just a computational difficulty, or so I'm sort of wondering about, you sort of want to collect enough data at tree level to sort of see a pattern.
I think definitely, going to like multiplicity 6 or 7 at tree level would also be interesting to see the results there. The reason that we, prioritize 5 point and are now moving on to more of a loop level direction is just because we really want to see what's going on at 2 loops. At 1 loop, there's so many like simplicities to some of the algebraic structures that we don't want to find patterns that don't really exist but just happen to show up just because there's really simple structures there. We're sort of hoping to focus on 2 loop and above as places where if there really is some sort of hidden structure like there was at tree level, we'd be able to see it and know it wasn't just a nice coincidence. But yeah, like going onward, say to 3 loop, we'll also want to have stuff like 6 point and 7 point tree level. And it'll be interesting to see how these sorts of like new color factors manifest there as well.
Yeah, I mean, just naively for me, I always think of 4 and 5 as a little bit special because you can always go to a half ladder basis, but 6 point, once you start going higher, you can't. You start having these weirder looking graphs that.
Yeah, definitely. I think it'll be interesting to see what happens at 6 point. My hope is, since we're always doing it, functionally, and we can take those weirder graphs and Jacobi them back to the half ladder, that these structures will continue, but we'll have to see. Yeah.